At a given instant in an airplane race, airplane A is flying horizontally in a straight line, and its speed is being increased at a rate of 8 meters per second squared. So A's acceleration is 8 meters per second squared. Airplane B, flying at the same altitude as airplane A, and as it rounds a pylon, is following a circular path of a 300-meter radius, given right here in the picture, 300-meter radius. So for airplane B, rho is 300-meter radius. Knowing that at the given instant, the speed of B is being decreased at a rate of 3 meters per second squared. So B's acceleration is deceleration. It is equal to negative 3 meters per second squared. Determine for the position shown, A, the velocity of B with relative to A, so find V, B with respect to A, and B, find the acceleration of B relative to A. So this is what we're looking for. We also know here from the picture that we have the velocity of A equals, it is flying horizontally in a positive x direction. We'll put our sign convention on here, x and y. So this would be 450 kilometers per hour in a positive I direction, and the velocity of B would equal 540 kilometers per hour. We have to look at we want to try to find an angle that is off of the x-axis here. So we want to try to find this angle, what that angle is. If this is 30 degrees, well, this has to be 30 degrees. And actually, the angle we really want is this one between our vector. But this would also be a 90-degree angle. So if that's 30, then this angle has to be 60. So 540 kilometers per hour. And then this would be the cosine of 60 degrees in the I direction minus the sine of 60 degrees j. So it's a negative j, a positive I and a negative j direction. So this, if we multiply it out, we get 270 kilometers per hour in I minus 467.7 kilometers per hour in the j. So there are different ways to do this, and there are solutions that are graphical where we can just add the vectors. So if we have our vector, somehow my pen has stopped working, but we can have the vector A and then add to it vector B and draw them to scale. So this is VA, this is VB, and then VA with respect to B. I'm sorry, VB with respect to A. We start at A and go to B in this notation. Would be here, and we can do this vectorially if we want, graphically, or we can know that the velocity of B with respect to A, or if you were an observer on A, what would the velocity of B look like? So from A, and we know this is VB minus VA, all done as vectors. So we have our vectors here in written out here. So 270 kilometers per hour, I minus 467.7 kilometers per hour, J minus 450 kilometers per hour, I. combining like terms, we end up with minus negative 180 kilometers per hour in the I direction, minus 467.7 kilometers per hour J. We can combine these. This is going to equal, using the Pythagorean theorem, 501.1 kilometers per hour. That would be the hypotenuse of the triangle given by negative 180 kilometers per hour I minus 467.7 kilometers per hour J. And then we can find our angle, which would be this way, 68.95 degrees. And that is the solution to part A. Part B, similarly, we look at our accelerations. The acceleration of A, so again we're looking for the acceleration of B with respect to A, and that's going to be the acceleration of B minus the acceleration of A. So first we have to find our vectors. So we have the acceleration of A is going to equal 8 meters per second squared in a positive I direction. It's increasing, so it would go in the same direction as the plane, and the acceleration of B is negative 3 meters per second squared multiplied by, it's in the angle of acceleration. It's 60 degrees, but because it's deceleration, it would be going in the opposite direction. It is an angle like this, 60 degrees. But we know that vector the tangential component. So this is the tangential component, and this is the tangential component. We remember that the acceleration, the normal component, I'm going to write it over here because right over here we can write the tangential acceleration is dv dt, and the normal acceleration is v squared over rho. So in the case of A, rho is infinity because it's a straight line. So if rho is infinity, then the normal component of acceleration, the normal component of acceleration for A would be 0. And the tangential component here of acceleration is given by the change in speed, which we were given here. So that's the tangential component. For B, the normal component would be v squared over rho. We have to convert 540 kilometers per hour to meters per second. This equals 150 meters per second. If you have trouble converting that, then please ask for help on that. But 150 meters per second, quantity squared, divided by rho, which in the case of plane B is 300 meters. This will give us 75 meters per second squared. And the normal component is always directed towards the center of rotation. So the normal component would be directed in this direction along this line. And that angle with the horizontal here would be 30 degrees. So we can add these again, VB minus VA, I'm sorry, the acceleration of B minus the acceleration of A So the acceleration of B with respect to A would equal 3 meters per second squared negative cosine of 60 degrees in the I direction plus sine of 60 degrees in the J direction. And then we're going to subtract from that 8 meters per second squared I made a mistake here, so we'll just go back and erase this, and then that is just the tangential component. I forgot I missed the plus 75 meters per second squared times the cosine of 30 degrees I. This would be negative, minus the sine of 30 degrees J. 3 meters per second. Yes, so that's actually just vector B, and then from that we're going to subtract the vector for A, which is minus 8 meters per second squared in the I direction. Multiplying all that out and combining like terms, we end up with negative 74.45 meters, or I, minus 334.9 J. All of that is meters per second squared. And we can use the Pythagorean theorem to find the combined vector. And I get 82.22 meters per second squared. And then we can use the inverse tangent. And I get an angle of 25.11 degrees.